And I heard from some of you, I think, a very uh, excellent point, that pointing out that I've really been going kind of perhaps much faster than was really a good idea. Especially the last couple of weeks, I was covering a lot of material. There's a lot of stuff in this book, and it's maybe faster than any reasonable person could be expected to kind of follow this. And I'm not having enough time here to actually explain this carefully to you. So let me. The good news, I agree. I agree that that's been a problem the last couple of weeks. But the good news is that we're now changing to a really different topic. And this topic, I think the next few chapters, chapters 10, 11, 12, are actually going at a much slower pace. And a lot of the new ideas in here are also they're much more standard things, which you've from the physics point of view, you should have seen if you've taken any kind of quantum mechanics class at all, because we'll be talking about just about free particles, and it's kind of the beginning part of almost any physics class in quantum mechanics. And then from the mathematics point of view, the crucial tool that we're using, which you're also using in physics, is Fourier Analysis. So if ideally, if the mathematics we're doing is not, is something that's actually a fairly standard topic in mathematics classes. Unlike the things that we're doing on the notion of a unitary Lie algebra representation, is something that I wanted to bring into this class because it really is the right. I really think it is the right way to think about the mathematics that's going on here. But it's something which I can't point you to a lot of good places to go read about if you're having trouble with it. It was it's a pretty tricky piece of mathematics, and it's not something that's normally explained at this level. Whereas the mathematics that we'll be doing for the next couple weeks, it is actually much more straightforward. It's just kind of a standard. It's the notion of a Fourier transform is a standard thing, which there's lots of books about. There's lots of places you can go read about it if you haven't seen it before. And we're just going to be using some pretty basic aspects of the Fourier transform. So I'm hoping that the next. So apologies for the last couple of weeks where there was perhaps I think too much being thrown at you too fast, and I'm hoping that this should not be true for the next couple of weeks at least. And then let me know if let me know what you think. I'd like to hear from you. Okay. So let's get started on the new topic then. And so today what I want to do is tell you about momentum. And also kind of justify, provide some kind of justification for the for kind of this standard thing. Maybe let me just write this. Yeah. Okay. So today please tell momentum, and try to really explain, kind of motivate the notion of what momentum really is. It's in physics, this is something which is kind of normally kind of a just kind of a basic quantity, which is kind of assume that you have some kind of physical understanding of it, but it's just defined, and you have to kind of deal with this. I think from the point of view of the mathematics I'm trying to explain here, momentum has some. Maybe I actually said this before. So we saw, and so this was kind of encoded in the Schrodinger equation that I h bar d t psi is equal to h psi. So this was called the Hamiltonian operator, and we had it had its eigenvalues. These are energy. So its eigenvalues have a physical interpretation of what if you're talking about the energy of a system, you mean that you've got a state which is an eigenvector of the Hamiltonian, and its eigenvalue is that energy. But this was really it's kind of a matter of definition. Was the Hamiltonian is the operator that makes that does this. And it was kind of a matter of a basic postulate of the theory that if you wanted that the problem of how to understand time evolution of a system could be put in this form for some Hamiltonian operator. So that was time. But now here, so now one way of thinking about what I want to say is I want to just say that we're gonna ask, well, what about what happens if not if you translate in time, but if you just translate in space. And so I h bar ddx psi is equal to p. And this is going to be this will be the momentum operator. And the eigenvalues are the momentum. Okay. And so I'll explain it in a minute. I'll say something about why we choose a different sign here. I mean, this again, this is just at this point it's the definition, but the point is that the momentum operator is exactly the operator that tells you, how to do an what happens if you infinitesimally move your system in some direction at x. So if you've got several different directions, there'll be a momentum operator for each direction. But for now, we'll just work in one spatial dimension, and then this is actually in some sense the definition of the momentum operator. Okay. And again, and the eigenvalues would be the eigenvalues of this thing. Okay, so now maybe before I do this, and then maybe to say where this is all going then. So what you want to do, so this is kind of, how things. I mean, there's only one momentum operator. So there's only one. So the momentum operator in all cases for any kind of quantum system will be the thing that tells you how, it's just this operator tells you infinitesimally how it happens as you move in space. But this is always true. Now the problem here is that you have to figure out how you evolve in time, how a system evolves in time. And this is just kind of geometric. Just whatever the geometry of how you've decided to describe states and their dependence upon where you are in space. However you're describing your states, you're going to get that'll define the momentum operator for you. This is what physics is called the dynamics. This is what's going to happen if you're in a certain state at a certain time. What's going to happen later is given by this, and h. And this is going to depend upon the physics, upon what kind of physical system you're doing. So this depends on the system. Okay. Whereas this guy is just kind of just depends on the fact that on the geometry of space. So what we're going to do is we're going to say, so we've in some sense said all. You can kind of say, well, we're going to talk a bit more about both of these cases, and then what we're going to do is say that for you're going to find the usual. I don't want to write this. Oh, okay. So we'll derive that. Let me say this. So we'll derive the usual Schrodinger equation for a particle in a potential by setting H. Okay, so so the physical assumption is going to be then that you know, okay, this guy's H is going to tell you about the energies. This is going to tell this is telling you about the momenta. And if you assume that these energies and these momenta are the same things that you heard about in your high school physics class, then you find that then the energy has to have the have a kinetic energy component, which is just, and the kinetic energy is a half the mass times the velocity squared, or it's the momentum squared over over 2m. So it's H is going to be p squared over 2m. Okay, and so and this is what this is mainly what we'll be studying for the first part of this class, where H is just, this is what we call the free particle. And then to make the problem more interesting and more complicated, you can assume that the particle, so this is just the kinetic energy. So you assume that the particle actually is moving, is being affected by some kind of force and coming from some kind of potential. And then you just put the potential as part of x. And then this as an operator, this is just okay. Actually, so I'll have to say, this depends on x. So this depends on x. And so we'll describe this more later. So next week we'll get to kind of how you're going to talk about, how you're going to put some function of x into your Hamiltonian. But this, so leave this around. And for today, actually for a while, we're just going to be thinking about this. We're just going to be thinking about something which is a free particle, and if you like, its energy is just its kinetic. It means its energy is its kinetic energy, and if you and the motivation for this thing, and you can motivate the equations governing this just by saying that I'm going to use the kind of standard classical non-relativistic version for the relationship between energy and momenta, and then just make it a relationship between these operators, and then and then when it will. If you're in momentum eigenstates, then the energy will just be anyway. Then you'll have the energy will be p squared over 2m, and it'll just be the kinetic energy of a particle. So that's the kind of, this is kind of the physical motivation of where we're going. And I won't. And you can kind of see if you take this, if you plug in for p here these derivatives, you get that this equation becomes IH bar ddt of psi is equal to 1 over 2m times 2 of these derivatives times psi, and you get the version of Schrodinger equation that you often see. It's a second order differential equation related with a ddt over here and 2 dx derivatives coming from this over here. So so often in a physics book they'll start by writing down that equation, but I want to kind of motivate that by saying that it really comes from here, and what we really need to understand is p, or what's going on in this momentum operator. Okay, so now let's shift back to mathematics, and so what we're interested in. So far in this class, we've talked about the group of the group U1 of rotations around a circle, and we've talked about SO3 and SU2 and rotations in higher dimensions. But we haven't talked about arguably kind of the simplest case of a group, which is just the group. Let's say this: the group of real numbers itself, under addition. So here we're going to take the group. So we'll consider the Lie group the Lie group, and so the group is just R, but the group law is just addition. So this, in some sense, and the Lie algebra, and the thing about this is that the Lie algebra. So you can think of this, of the Lie group R with addition. If you want to, you can think of it as acting on something. You can think of it as acting by translation on functions or on something else. And then the infinitesimal thing will be infinite. So this will be, you can imagine representing it as translations. And that's the kind of the representation we're going to be interested in. And then the Lie algebra is then also R, and then the Lie bracket is 0. So it's a trivial Lie algebra with just one-dimensional Lie algebra, and its Lie bracket is 0, and this is going to be infinitesimal transform. I mean, if you think of so the derivative of a translation is just an infinitesimal translation. Derivative of okay. Now, if you want, you can you can write as a matrix group if you want. So instead of thinking of R with the additive group law, you can think of so one write down so A, for A some real number, you can and you can think of real numbers with the additive group law. You can instead write them this way: 0. Okay, so write it as 2 by 2 real matrices, and then you use the fact that then use the matrix group law multiplication. So I won't write this out, but you can see that if you multiply, well, you can see that. No, let's do it. If you write this. Okay, so you can think of instead of just thinking of this with A, anyway, that the group multiplication is just A plus B. Well, instead you can, if you really have grown to love thinking about groups in terms of matrices, you can do this. Okay, and then the nice thing, then the Lie algebra, to get the Lie algebra, use this definition that the Lie algebra is stuff that you can exponentiate. That if you got a matrix group, the Lie algebra is the space of things that you can exponentiate to get these guys. So then you just have, this will be these are elements of the form this. And then because then what you do is you use the fact that e to the 0, A, 0, 0. I mean, if you write this as an exponential, it's going to be 1 plus this guy, so it's going to be 1, 1, 0, 0 plus 0, A, 0, 0 plus everything else is 0. If you start multiplying this guy by itself twice or more times, you're going to get 0. So this is and this guy is clearly is, well, anyway. This guy is just this guy here. So anyway, so this whole formalism we've been talking about Lie groups as matrix groups and Lie algebras as spaces of matrices, as linear spaces of matrices that you can exponentiate to get the Lie group. It all works here. It's often not really a And it's sometimes useful to kind of go into this language to try to make sure that you're understanding how the whole language of Lie algebras and Lie groups or representations is working in this case. But on the other hand, it's a bit silly because all you're doing, the group law really is just addition. And so you don't really need to think about it that this way. But the thing that's confusing is the thing that's a bit confusing is that the Lie algebra, so the Lie group is R, group is the real numbers, and the Lie algebra is also R. Okay. But you have to realize that this is a group. It's got this additive group law. This as a Lie algebra, this is just the Lie algebra with the Lie bracket 0. And the exponential map in this case is also, notice that before when we talked about the exponential map, like even on U1 or on matrices, the exponential map was not an isomorphism. Like as you go, your Lie algebra was a real vector space, and then if you exponentiate it, you get this kind of curved Lie group. Here, when you exponentiate from the Lie algebra to Lie group, you're just taking R goes to R. So we're often going to just use the same coordinates on the Lie algebra, and so or often we're going to think of the coordinates on the Lie group are just the same as the coordinates in the Lie algebra. Or if you like, we're going to think of the exponential map as just identifies these two guys. Okay, so now that's that. Now so this is the group theory here. The group theory is really trivial, or you can turn it into matrix group theory, which is slightly not much more non-trivial. But now let's see. What we want to do is we want to ask about representation theory. Okay, and so what are the representations? Well, let's start by asking what are the irreducible representations. Okay. And remember, so this is a commutative group, so they're going to be one-dimensional. And if you actually go back and look at what we did at the argument that we had for U1, the argument we had for U1 started by, anyway, it starts out in a certain way and says that you have to get exponentials, and then it imposed the periodicity condition, and then that meant that those exponentials had to be an I times an integer. Well, in this case, so this is just the same argument as for U1, except that you don't accept no periodicity. So the argument starts out as the same. If you go back and look at the argument for U1, it starts out the same, but then you never get to the point where you impose a periodicity condition. And so what you find is that so they're given by a C, so by some complex number, and pi of A is equal to e to the CA. That's all. This is pretty trivial. So you're getting one-dimensional representations, and pi of A, and again, yeah. So we're A labeled some point in the group or a point in the Lie algebra equivalently as pi of A CA. And they're unitary, right? If C is pure imaginary. So if these are purely imaginary, you get a unitary representation. If they're pure imaginary and an integer, then you get period of C2 pi and you get U1, but there's not. So the difference in U1 is that you get is that no integrality. So there's no, these are no longer integers, but just kind of arbitrary, pure imaginary numbers. Okay, and then let's see, okay, so then what happens is that now, okay, so these are the one-dimensional representations, but what you're interested in. Okay. So we're interested in in an infinite dimensional representation. The functions on R. Okay. So these are the one-dimensional irreducible representations. But what's about to happen now is that we're going to start. So what's to be going on now from the point of view of representation theory is that we've decided that by that motivation of saying that that the momentum was an infinitesimal translation, if I want to interpret that momentum as that momentum operator as a Lie algebra representation operator, I want it to be given by infinitesimal translation, and it has to be translating something. So we're gonna be talking about the simplest thing, which is functions in the real number line. Let's say complex functions in the real number line. And so we're gonna, at the end of the last section of the class, I started by writing. We were looking at SU2 and SO3 representations as representations on an infinite dimensional space of all polynomials in Z1, Z2, or all functions in the sphere. But what happened there was that when we broke it up, we could break it up discretely into these irreducible discrete pieces, and those were finite dimensional. Those, as you saw in the exam, you could write in terms of matrices if you wanted. But what's going to happen here is we've got an infinitesimal representation, and the irreducible representations are going to be one-dimensional, and so we're also going to try and break up the representation into these irreducible one-dimensional pieces. But the problem is going to be that in the U1 case there was a nice finite there was a nice they had this nice discrete. They were just labeled by discrete parameters, so you can imagine putting these discrete things together and taking them with various coefficients. Here, the parameter is going to be not discrete, so you have to, in some sense, here all of a sudden you're going to have to start doing analysis. So what I'm going to be talking about, especially next time, is more kind of some of the basic analysis you have to do. And here are, this really is. You can't. Anyway, we really do have an infinite dimensional representation. It turns out, but it's going to be a representation on functions, and then our Lie algebra, and then so R acts by translations. And now I think I'll change to the variable I'll use to describe the real number line here is Q. It's the standard physics thing for a position. So Q goes to Q plus A. It's a translation. And then it acts. So then the representation. So it acts on functions. And the way I've set this up is that pi of A acting on f of q. So I've done this kind of standard trick of taking the inverse of the inverse of the action on the space itself. This is commutative, so there's actually no need to do that. But for consistency with kind of non-commutative groups, I've done this, which is this. Okay, so the group R acts on the real number line this way, and it acts on your infinite dimensional space of functions this way. Okay, and you can show that this is a representation of R on the infinite dimensional space of functions. And the
I just have a quick question.
Yeah, sure.
So is it that there are finite dimensional representations, but they're just exactly analogous to like how we constructed the U1 representations with this different except with this E to the CA instead? Or is it?
We'll get to them in a second, but yeah, I mean there are one-dimensional representations, and they're actually and those are actually going to be your eigenstates with a well-defined momentum, and we'll get to them in a minute. But I think the thing is, what we'll see is that what's really non-trivial about it, becomes really non-trivial about this whole subject is not the one-dimensional representations are just like the U1 case. They're important, but the whole subject becomes really non-trivial because you want to if you're given you really want to work with arbitrary functions, not with these functions, and so you have to you have to decompose arbitrary functions into these functions, and that's the whole subject of Fourier analysis, and it's kind of non-trivial. Okay.
Okay, so I guess that's what I meant. It's just that's the non-trivial. That's the only like non-trivial.
Yeah. So far everything so far is trivial, but there's some kind of new thing which we didn't see in the U1 case. In the U1 case, since everything was discrete, you just had kind of a discrete problem of how to add. I'm just adding, or maybe the thing is to say in the U1 case, I could talk very nicely about saying, oh, my representation was, what was this direct sum this direct sum this. The problem here is that here you need. You're not adding together a discrete number of things. You're typically adding together an infinite number of things. So you need something like something more like an integral or something. Okay. So this is why So this is just to say why we're gonna, we're gonna have to enter into some mathematics we haven't seen before. But it's standard. It's going to be a standard analysis.
Thank you.
Any other questions about this? And maybe, and then quickly just to say that then the if you take the derivative of this, and now also notice that I've done a funny thing. The slightly confusing thing I'm doing is I'm using the fact that the exponential map identifies the Lie algebra in the Lie group, and I'm using the same coordinates on the Lie algebra as I am on the Lie group. And here it means, but here it's kind of the exponential, is it? So here. But anyway, here it's an infinitesimal translation, if you like. It's a thing that you exponentiate to get this guy, but they're both copies of R, so I'm just using the same notation for this. That takes a little bit of getting used to. But if you work out what this is then just minus A times ddq. And it's just so what you're doing. So the way the representation is acting on a function is by translating the negative direct by negative A. So the infinitesimal action is just going to be, taking the derivative. The derivative is just an infinitesimal translation, and then the kind of the amount by which you're anyway. So the A appears here as your. Anyway, so then you have to have an A here, so that this is a linear map. This is linear in A. Okay. But these are, this is the representation, and the only now and if you're used to thinking about analysis, you're going to now you're going to go, wait a minute, but he hasn't told us which kind. What kind of functions are you talking about here? And if you're, and in physics, you often, well, anyway, so a lot of what I'm going to do next time is kind of give you, try to make some precise statements about what this actually, so here I've in some sense defined the representation that we're interested in. It's an infinite dimensional representation of R, and it's an infinite dimensional Lie algebra representation of R. But I haven't really completely specified it because I haven't told you which kind of functions we're talking about. And we need to do that. Okay, let's see. Maybe, what else I want to tell you? Okay, so now let's go back to this notion of momentum. So now we're going to define. I already gave you the motivation for this at the beginning. So we'll just define momentum operators. And I think, I guess in the notes I started by writing this out in three-dimensional space, but now I'm just going to go, for now, we're just going to work in one dimension, because what happens in three-dimensional space is really just three copies of the same thing. You just have you can translate in three different directions, but everything commutes in the different directions. So let me give you the definition. The momentum operator on is, okay, P is equal to minus I H bar d dq. Okay, and I really to kind of to make this be some kind of a halfway legitimate mathematical statement, I have to tell you what this is acting, which space of functions that this is acting on. If you want, anyway, just because I want to get into that more next time, but for now you can think of, you could take, think of this as acting on H is a square interval. All functions. Although I should, that actually really doesn't help. Anyway, that actually doesn't help the matter, because then this just creates other problems of analysis. Okay, so let me just kind of say that there's a hole in this definition here that I'm not actually telling you what I'm telling you that this. So this is acting on functions on complex valued functions on R, but I'm not telling you which ones. Again, so there's a hole in this definition to be filled later. Okay. But you should think of it, the state space that we're working on now is now an infinite dimensional state space, but it's a very simple one. It's just the complex valued functions on the real number line, and we've defined this operator on them. And what I've said is that this is anyway. So I'm going to quickly stop writing H bars and go to units in which H bar is equal to 1. But every so often I'll write down. But up to this is really the Lie, as I kind of explained below, this is the Lie algebra. This is the algebra representation operator for the translation, so for the representation of R on functions on R by translation. So I didn't want to kind of, anyway, so what we're going to get away from this fairly quickly, but for now, I just wanted to connect this to what we've been doing before, where the argument was that the interesting operator is always going to come from the Lie algebra representation, and in this case, it's this one, but it's really kind of a really kind of stupid, very simple thing here. It's really just up to this minus I. It's just a differentiation operator. Oh, and then one thing to notice is that and again, what I've done is I've written this guy is self. The reason for the I is that let me just say this, that DDQ is skew adjoint. Like, for the usual inner product. Okay. So if I was kind of following my philosophy that you really mathematically, you should always be, it's best to think about the skew adjoint operators. Those are the ones that are really give you the algebra representation. Then I would just use this guy. I wouldn't multiply by this minus I. So the multiplication by minus I is to turn something skew adjoint into something self adjoint. And the skew adjointness just comes from this calculation, that the integral infinity psi bar 1. So if you take the inner product of two functions and then put your operator here, okay. So this is then this is the same thing. Then if you can rewrite this thing as an integral minus infinity to infinity of the derivative psi 1 psi 2, and then minus psi 1 the q the psi 2 dq. Okay, and then the point is that this guy. So if we're going to assume that these guys actually have some kind of well-defined inner product, then this psi 1 times psi 2. Sorry, this has to be here, and then here, and that this guy has to fall off at infinity. And so you're taking the derivative of something that's falls off infinity. So this is going to be just the difference between the value of this at plus and minus infinity is this is going to be 0. So this goes away. So this is equal to minus DDQ psi 1 times psi 2 bar. Okay, so this is just a very simple kind of standard kind of integration by parts kind of calculation, and it's the thing. It says that the operator DDQ is skew adjoint. That if you move it from here, if you move it from operating on this guy to operating on this side, it's the same thing but with a minus sign. And so if you want to, instead of working with the skew adjoint operator DDQ, if you want a self adjoint operator, the standard thing to do to get from skew adjoint to self adjoint is multiply by a minus I, and then anyway, h bar we could assume is 1. So that this comes from the units. This comes from wanting something self adjoint, and this is the basically algebra representation operator for the translations. Okay. Okay. So let's see what else I want to. So any questions about this? So this is the basic setup so far, and and I did the thing that I just haven't told you is what class of functions really, other than we need them to fall off at plus and minus infinity. Okay, so then what else? Okay, so let's maybe okay, so let me go back maybe to let me kind of end with maybe kind of the standard kind of physics calculation. Let's go. Okay, so H is so the description of a free particle And anyway, just for fun, I guess, let me then just write this for the true thing in 3 dimensions then. It's going to be H is equal to 1 over 2m P1 squared plus P2 squared plus P3 squared. Okay. And so these are, and Pj is minus I H bar D. I guess I'll stick to using Qj, right? And so then the Schrodinger equation, and the motivation for this again is that this is just the if this is going to be energy and this is going to be momentum in the classical sense, then then the kinetic energy of a free particle is the sum of the squares of momenta divided by 2m, or half the sum of the mass times the velocity squared. Okay, and so this guy. Okay, but now you can think about this guy, acting on this representation on complex valued functions. Now on R3, you would say that this guy is if you square these guys, you get a minus and an h bar, so you get a minus h bar squared over 2m times the derivatives. Q squared plus Q3 squared. Okay. So this is now a second order different. It's a second order differential operator acting on our states as functions, and then the Schrodinger equation or equation. It says I H bar d dt is so now we're gonna act. So this is acting on on complex valued Q vector P. So our states are going to depend upon points in R3, and they're going to evolve in time. And so psi of Q vector T is minus h bar squared over 2m d squared dq squared. Anyway. Okay. So this is then what you see in pretty much, you'll find a long description of what's going on with this in any physics textbook. This is often kind of the starting point in a physics textbook, is to kind of take some kind of to try to find take some physical kind of motivation for how to why this is the right Schrodinger equation to describe a free particle. And I gave you a somewhat different one, but then the solutions. So the way physicists then approach much more the subject is they approach it that the subject is really being a subject very much about differential equations. That everything that typically you're given a problem to solve as a differential equation, and then what you're going to do is you're going to throw at it the methods you know for solving differential equations. And so from that point of view, one way to say this is you can look for. So one way to do this is to look for equation. Well, anyway, so let's just say it this way: look for equations, look for solutions that are a product of a function of Q, and function of P, And so these are called, you say this is a separable equation. You look for separable solutions to this, and then what you find, maybe I should just write out the answer to what you get. Is you get then that you get find solutions. So e to the, how do I want to do it? I want to write this as e to the, as psi of q vector t is equal to e to the I h bar t e for some e, and let's call it e and k vector. E to the I. Now I've got to get a I want this k vector. Okay. And these have where and where here, let's see, so and here, and to make this be a solution, you need E is, so what you have is that P vector is H bar K vector, and you have here that E has to be P squared over 2m, so it's H bar squared over 2m m times the absolute value of K vector. So these are solutions. So you have solutions labeled by K vector. It's essentially the momentum in that P vector. So P vector equal to H bar K vector. So these are H and P vector eigenstates, eigenvectors, and so this is the momentum, and this is the energy. And so I guess I better stop with this here now. And so what I've done is I've written out. So this is these are the one-dimensional solutions of the Schrodinger equation, and they really kind of correspond to finding the irreducible representations of the translation action. That's these guys. These are your irreducible unitary irreducible unitary representations of the translation action, and then just then the court they each give a solution of the Schrodinger equation this way, and as long as the energy as the eigenvalue, as you said, because of the relation H is P squared over 2m, you have to have this has to be true. Okay, so let me then stop here. But then the problem, how do you decompose? You decompose a general solution in terms of these solutions that are labeled by these parameters K. K vector, and this is going to be essentially this problem is essentially the problem of the Fourier transform. Yeah. So what I'm going to do, what I'll talk about next time, I guess I'll stop here. And then what I'll talk about next time is really going to be, basically mostly kind of mathematics. So it's mathematics which is crucial and crucially shows up in any physics course at this point, which is the mathematics of how you how you do this. If how do you talk about general functions and decompose them in terms of these guys, and that's the whole story of the Fourier transform. So next Tuesday will be kind of a lecture which will be more kind of a lightning course in the Fourier transform. And at that point, I'll actually try to make some precise statements about exactly which kind of functions we're talking about. And you quickly find that this is the analysis here actually is just trickier than it seems, and that you really need you need to think a little bit about things that are called distributions. So we'll quickly go over what a Fourier transform is and what a distribution is next time, and that'll give us the kind of mathematical apparatus we need to kind of to work with these things. Okay, so any questions about any of this stuff? No. Okay, I'm hoping that if you've had a physics course, this should all look very, very, very easy. If you've had next time, if you had a Fourier analysis course, it should look fairly easy. But it's the one new thing that maybe you haven't seen is just the interpretation of the argument that you really are supposed to think of the momentum operator as the Lie algebra as up to a factor of minus I, the Lie algebra representation corresponding to infinitesimal translations on functions. Okay. Anyway, and I promise by sometime tomorrow I'll get all of your grades entered. I mean, but in general, I should say I'm pretty happy. People seem to be following what's going on here, and mostly the only problem people were having was finding the time to do something with the trickier fourth part, which is not unreasonable. Okay, so I'll shut this down now, and if you have any questions, come back in a little while, or else if not, I'll see you all on Tuesday. Or if you have any other questions about the exam, you can contact me separately if you want to talk about that. Okay, well then bye for now.
Thank you.
Bye.